thank you very much for that very kind introduction. Certainly excited to be here today. Now, I'm a Volts and Amps guy, so I am usually very geeky, but for this morning's session, I'll try to, this afternoon session, I'll try to keep it a little bit higher level. And I'll leave the really geeky stuff for the experts that will follow on afterwards, Jason, Julia, and all the others. Now, maybe just to start off with, I'm very excited about this particular topic. Now, 25 odd years ago, when I first started my career as a graduate engineer at ABB High Voltage Technologies in Switzerland, one of the first projects I became involved in was a power quality product that was that's called a dynamic voltage restorer. It was a medium voltage series connected device, only about 4 MVA in rating, and it was using, at the time, integrated gate commutated thyristors in order to inject a series voltage to correct voltage sags and temporary supply interruptions to protect sensitive loads. And one of the challenges was the development of the phase lock loop that would ensure fully capable of 3-phase correction, even for unbalanced faults, and to manage the voltage wave quality. Now, the DVR had enough energy store to restore voltage sags in a single phase up to 50% for about half a second, or a lesser duration and depth across multiple phases. Now, beyond this level, the energy storage would usually run out too quickly, and I do remember and recall that both deep sags and large phase angle jumps could create issues for the controller, which made it quite challenging to integrate. Now, back in the mid-90s, this was considered to be quite a significant and advanced application of power electronics. I mean, at the time, we still had high voltage DC and static bar compensators using thyristors, they were line commutated. IGBTs were only just starting to develop the current rating and carrying ability that we see today. And advanced inverter applications were still largely confined to microgrids. So why all of this? Well, if we fast forward a few decades, and by now we're seeing solar farms of multiple 100 megawatts connecting into the grid at some very weak locations. And back in 2016, when I was working at AEMO, we already suspected that there were going to be some issues. South Australia had just experienced its first blackout for many years. And while that wasn't directly related to renewables, there was some unexpected behavior with some of the equipment that did send us down the road of doing some more detailed analysis of particularly inverter-based resources. In the northwest of the state of Victoria, which is next door to South Australia, is an area that in some circles has been called the rhombus of regret. It's so called because of the trapezoid shape of the 220 kV lines that bound that region. Now, the area has attracted a lot of attention from renewable developers, and in the past years, because of its high solar irradiance, because of the good wind speeds and the very flat land that is in this area, there has been a lot of renewables built, particularly in the north with solar and in the southern part with wind. Now, around this time when we're first noticing some issues or suspecting some issues, there'd already been some instances of some oscillatory behavior reported anecdotally. The voltage oscillations of around 4 to 8 hertz magnitude that had been observed in an area just north of the Murray River, which is the area bounded to the north of the rhombus, had reported some oscillation when they were doing simple line switching for the purpose of maintenance that resulted in some adverse interaction between a solar and a wind farm, both inverter-based resources connected to the 220 kV system there. Now, the initial analysis that we performed suggested that this was because of the relative proximity that we saw there. And similarly, then, when we did analyses of the rhombus region, the 500 or so megawatts that were connected in the area, in combination with simple impedance changes caused by, say, line switching, was enough to excite voltage oscillations of around 8 hertz and lasting for as long as the impedance had changed. The oscillations will only subside when we actually switched the line back in and restored the network impedance. Because of the potential security risk that this presented, the solar farms were constrained to about half their capacity while we were working and trying to figure out how to sort of resolve the matter. But in the meantime, while we had constrained the existing solar farms, there was still a lot of new generation backing up to connect and seeking to establish themselves in the area. But these projects had to be put on hold and eventually had to be queued unless they were able to remediate the projected system strength shortfall that would result in the area when they did interconnect to the network. Ultimately, it was a combination of a wide area tuning exercise for the inverters in question here, and the installation of some synchronous condensers that allowed those particular plants to be able to restore to their full capacity. Still, though, the story doesn't really quite end here because there are still spurious oscillations that occur which haven't been, or the source of those haven't been located. Now, these are a little bit high frequency, at about 19 hertz, but they come and go, and it's been very, very challenging for EMA to actually find the source of those. Now, the lesson here and the problem here is that in Australia, these issues have resulted in some slowdown of rates of interconnection at a time when we needed to replace a lot of our thermal generation that is starting to withdraw. There's been a lot of announcements in Australia recently of withdrawal of the thermal plant, as well as presenting the technical challenges of renewable integration and managing to operate the system stably while we're doing so. And I'm sure that there are similar stories that you guys will be familiar with. And while every region is very unique in its challenges, the root causes are often quite the same. It's low system strength and a high concentration of grid-following inverters. So grid-forming inverters, synthetic inertia, virtual synchronous machines, advanced inverters, it's a lot of buzzwords around the new technologies we're looking to put in. And it's pretty much looking at just the voltage magnitude and frequency controlling inverters that have been used in microgrids for quite some time. Notably absent, though, is the application of these inverter technologies to the main grid. And I suspect due to the complexity of the design and the operation when it is interconnected with other equipment and the dynamics of large power systems. However, back in 2017, the South Australian transmission owner, Electronet, commissioned a ABB advanced inverter at Dalrymple, which is located on the Lower York Peninsula in that state, and located near the tail end of a very skinny 132 kV line that supplies a load that varies from negative to positive depending on the output of solar rooftop in the area. Additionally, at the very tail end of the circuit that extends out of that Dalrymple substation is one of Australia's first wind farms, the Wattle Point wind farm, built in 2004. And rated at about 90 megawatts. Now, the battery was built by an ABB team that had been building microgrid and standalone inverters and transferred a lot of that knowledge into the design of the application. And Electronet had commissioned the work because they were looking for this battery to provide reliability and to strengthen a portion of their grid that had often been experiencing stability-related issues and disconnections. Interesting, though, is that the battery is actually operating in a grid following mode when it's synchronized and only falls over into the grid forming mode when it is silent from the main grid itself. And this has happened several times, showing that there is a very fast and very capable transition and flexibility of this technology to switch between these two modes to supply the load and to connect customers in the island network and to reconnect, synchronize, and then follow the grid when it's reconnected. And so while it's not a true permanent grid forming battery in every sense of the definition, it certainly has proof that the concept is very much developing and proving to be successful. And the battery itself also did kickstart a lot of interest in the advanced inverter R&D and implementation works. And the NEO Tesla battery at Hornsdale, also known as the big battery, also located in South Australia, some distance from the state's capital, Adelaide, is located within a very high wind penetration region of the system, initially built as a 100 megawatt plant, 129 megawatt hours, grid following inverter, and it was used to provide all sorts of services from frequency regulation to participation in the system protection scheme a wider area, fast-acting emergency frequency control scheme. It was constructed initially in 2017, but then 3 years later, they expanded the capacity of the plant by about 50%. And this additional 50 megawatts and 65 megawatt hours was installed using an advanced inverter design that Tesla refers to as their virtual synchronous machine. And it will provide frequency responsiveness and some inertial input. The initial construction was to test the concept, and then eventually the entire facility was to be transferred and transitioned to this new mode of operation. And Neoen, the owner of the plant, has already reported some successes when in May last year there was a explosion at Central Queensland power station at Callide, some distance of 4,000 kilometres away, that caused a fire and disconnected the other units in the same station, and then subsequently, a short time later, other plant nearby. Now in total, the NEM lost about 3,000 megawatts of generation, quite significant for the time, and caused a frequency deviation of more than half a hertz that was felt throughout the entire interconnected national electricity market. And as I said, some 4,000 kilometres away at Hornsdale, the advanced inverter battery responded very much instantaneously and in a very frequency responsive manner. That Neoen claims is the proof of the design. And whether or not this is true, it did perform extremely well, but I feel that we probably will need to wait a little bit more for some events to prove this conclusively. And as they say, they never waste a good crisis. So why is all of this important, this development of technologies and this transition and resolution of issues? Well, if you look into Australia's or the National Electricity Market's integrated system plan, which is a 20-year outlook and coordinated transmission strategy for the market itself, this year's draft is presenting quite a stark and challenging picture. That we'll see the withdrawal of about 23 gigawatts, the last 23 gigawatts of our coal-fired generation by around 2040, and see a very steep rise in the amount of intermittent inverter-based resources that's driven mainly by wind and solar PV at the top end of the transmission level of town, and by distributed solar photovoltaic throughout the distribution system. And in fact, that same document suggests that we're going to experience penetration of up to 100% renewables by that 2030 under the step change and quite steep scenario a little bit later, but the hydrogen superpower, which will really see a lot more renewable penetration coming through. We will see those penetration levels reach 100% quite early. In fact, we've already had 50% penetration levels during the shoulder seasons, that is spring and autumn. And in some regions of the network, such as South Australia, we've already produced 140% of local demand, the rest then being exported. Now, we'll still expect to have dispatchable generation available for some time, mainly in the forms of storage, whether this is batteries or hydropower or some other form of storage. Ultimately, though, we are going to have to look into our power system engineering toolbox, and we will find probably that we're going to have less synchronous generation and more asynchronous intermittent generation. This is really going to drive a lower system inertia, especially for a frequency event that's going to be important, and a lower system strength, which, if we continue in the pathway of grid following inverter technologies, will be quite challenging. So the question then is, how do we build a bridge to that far shore of a all inverter based system? Now, according to AEMO's engineering framework that was published in 2020, and then followed up with the Advanced Inverter Whitepaper that was published in 2021, that is last year, the things we want from advanced inverters include the ability to operate stably in low system strength frameworks, but not only that, but also to be able to contribute effectively to system strength. Furthermore, we want to see these technologies being able to control frequency and to contribute to the inertial response of the system, the latter of which is currently provided by the rotating masses of synchronous generators that obviously won't be there one day. And ultimately, we want them to be able to restart the network if we have a blackout. In fact, we're really looking for them to do everything that we currently get from synchronous generators, but faster. We don't have to do it quickly because the integrated system plan indicates and predicts that while we're still relying on 23 gigawatts of coal-fired and some 20 gigawatts of gas generation in Australia, as well as various forms of storage, that we are going to have to transition very quickly. And by the middle of the century, we're going to need about 45 gigawatts of storage, a lot of it which is going to have to be based on some advanced inverter designs in order to make sure that we can still manage the system securely. But in Australia, at least anyway, there are signs of progress. The Australian Renewable Energy Agency, for example, has announced some very significant funding that's being made available on a competitive basis for advanced inverter applications that are greater than 70 megawatts. So we're looking at the big stuff rather than the smaller aspects of the system. And while the $100 million that's being made available doesn't seem like much, it's actually good to recall that the EPRI and the Hornsdale Power Reserve batteries received less than $20 million in order to get up and running. So the funding and the seed funding that's provided here is likely to see some very large projects get moving and get up to speed. And given that I think there's roughly about 5,000 megawatts of large scale batteries either planned or announced, and many of these are proposing to be of grid forming types. And such initiatives, combined with the fact that we're here speaking about and collaborating on these topics, and I saw the ESIG working groups publication just last week on advanced inverter concepts, is actually to me a fantastic sign that we're making that great step forward in order to transition and involve our power system. That concludes. I'm happy to take any questions or comments or thoughts. And in the meantime, I thank you very much for listening.
Okay, so let's go ahead and move into our official session that Jason MacDowell of GE is going to chair. Jason is also the chair of our reliability working group at the ESIG, and he's been leading the charge with Julia on the report that you saw come out last week on grid forming inverters. Been a big piece of work over the last year, and will continue in that area over the coming year. So, Jason, I don't know if you want to bring up your people one at a time, or?
Yeah, let's have all the panelists come up.
Oh.
Great. Julia, Deepak, and Vahan, would you like to join us up here? Great. Yeah, this is
Set up. Maybe it's set up. You're all set.
Well, good afternoon, everyone. Welcome to, I think this is the first all in-person panel. We'll see if we can remember how to do this face-to-face instead of virtually now. I was talking to the panelists, and it's certainly nice to be back face-to-face with everyone and being able to see everyone in 3D and interacting like we've done. It's certainly been a long time, and it's a pleasure to be here with all of you. I'd like to really talk about a deeply important subject around technology integration. You know, we talk a lot about the aspect of how grid integration works. We certainly talk about adequacy. We talk about the different levels of penetration and how planning is done. But really the precipice of how to make all that work in the beginning is having the technology and the capability out of resources to be able to do that. And there's a cycle that we're going to talk about over this afternoon that our panelists are going to address. So we have a really great panel session with world-class panelists, rock star panelists. In this session, we're going to talk about more about where we are today and where we're going tomorrow with grid forming capability and new technology deployment. And then after this, we're going to have another session on grid forming about some practical aspects. Really, I think we're going to have like Charlie said, a very deep and weedy discussion, but also pull it back to how does this matter, right? And how are we actually going to get all of these new capabilities deployed on the grid, how it's needed, when it's needed, and make sure that we're addressing all the needs and the problems that are worth solving, right? So I really, before we get started, I wanted to just mention that all of the work that has culminated to this point around grid forming that we started, what guys, maybe 3, 4, 5, 6 years ago, talking about grid forming through IEEE articles that have been published, through different activities that we've started within the reliability working group. And just to see where we are today in a very, it's been nothing of miraculous to see how quickly a cycle we can go through to understand what the grid needs are, making the most out of the existing inverter-based resources we have today, and then identifying new services, new needs, new capabilities, and deploying them on the grid, right? So it's just miraculous. And I wanted to really acknowledge all of the great work that went into the formation of the grid forming report that was just released last week from the Reliability Working Group. And wanted to recognize that all of our panelists here today were foundational in their contributions to that report, as well as the all but one panelist and the chair of our next session were also very monumental in making contributions to the report. And certainly it couldn't be done without the leadership of Julia and the High Penetration Task Force. So really wanted to say special thanks to Julia for all your leadership. So without further ado, would like to start off and introduce our first panelist, Julia Matevosyan. Julia is ESIG's chief engineer and has more than 20 years of experience in the power industry. Prior to joining ESIG, she was a lead planning engineer with ERCOT. At her time with ERCOT, she worked on adequacy of system inertial response, system flexibility, frequency control, and performance issues related to high penetration of inverter-based resources. Julia received her bachelor's degree from Riga Technical University in Latvia and her master's and PhD at the Royal Institute of Technology in Sweden. And I have to say, I'd be remiss without really recognizing and identifying Julia's industry leadership in ESIG, at GPST, at NERC, at CGRE, at IEEE. All of these things are really coming together, and we're really seeing fantastic and fabulous results because of all the leadership that Julia has given to the industry. So I wanted to say thank you. So with that, I'll turn it over to Julia.
Thank you, Jason. Can you hear me well? All right. Okay, so you probably have seen in your mailboxes the report that's the picture of which you can see on the right-hand side. It's actually linked there, so if you go to slides, you can get to the report. So to start off, I'm going to provide overview of that report and kind of say what's in it, and then all the geeky stuff will follow. So if this is just an overview of where we are, it's a slide from NREL showing penetration of inverter-based resources in terms of energy in gray circles, and then in terms of instantaneous penetration levels in red boxes. So basically, as a one example, and I come from ERCOT as a home system. If you look at ERCOT bar, then it reached 66% instantaneous penetration and 26% energy. So basically, these numbers are growing. Some of the island systems are already hitting 100% instantaneous penetrations during some periods of time. So this is kind of just a reminder of history of development of inverter-based resources. What you can see on x-axis is some kind of representation of system strengths, let's put it this way, and so it's shown as equivalent short circuit level here. And then also on x-axis, you can see inverter-based resource instantaneous penetration. And then you can see this blue line that's showing difference between stable and unstable systems. So everything above the line is stable, everything below the line is unstable. This is just schematic representation how inverter-based resources were developing over time as more and more were integrated in the systems. So initially, as your system is strong, you have just lower percentages, maybe, I don't know, around 10–20% penetration than your off-the-shelf inverter-based grid-following resource will do. And then gradually some grid-friendly features were being developed, so providing frequency support, high voltage ride-through capability, and so on. As penetration of inverter-based resources is increasing, then weak grid features were introduced on some inverters. FACTS devices were used, control interactions, grid enhancing technologies were used to address some of the reliability issues as they started creeping up with weaker grid issues. And then as you increase even further beyond maybe 50% penetration, further control advances are needed. More often, tuning of controls is required in certain areas. And then synchronous condensers, as Christian mentioned, are being installed in some areas to provide stabilization. And as you go beyond maybe 65, 70% penetration, then you need to think about even more advanced inverter controls. And this is where kind of grid forming is becoming interesting to provide stabilization in really weak grid areas, ensure islanded operation for parts of the grid, enhance fault contribution. And so this is where some of the systems are already finding themselves today, say GB system, Ireland, Australian. And then also if you look at ERCOT system, there are parts of the system that are already there. And this is where grid forming technology can be helpful. And so grid forming, just a buzzword for advanced inverter controls. They're being designed to provide stabilization effect in weak grid areas and improve stability for existing grid following inverter-based resources in areas with high concentration of inverter-based resources. Additionally, if these resources are equipped with ample storage and maybe additional capability on the inverter side, they can provide additional functionality like inertial support, fault current, additional fault current injection, black start capability. But again, a resource has to be designed with sufficient capability to provide these functions. They can provide other grid services that grid following inverters can provide as well. And so this is just schematic that Andrew Isaacs was showing in the last spring workshop to show the difference between grid following and grid forming resources. So basically grid forming resource will hold its internal voltage and angle constant during transient time frame after an event happens on the grid. And with that, it will provide instantaneous injection of active and reactive current components as needed into the grid to support grid stability. And then grid following inverter will hold its active and reactive current components constant in transient time frame, and it uses some kind of stabilization function, usually PLL, phase lock loop functionality, to lock onto the grid and kind of follow the grid signal. So this, a lot of text on this table, but it basically showing comparison between grid following, grid forming inverters. So I just mentioned, grid following inverter will rely on stronger grid voltage signal to lock onto it and provide current control. And grid following inverter will actively maintain voltage magnitude and phase. And then in dynamic behavior, grid following inverter will look like current source in transient time frame, whereas grid forming inverter will keep voltage magnitude and phase constant in transient time frame. Grid following inverter will rely on some kind of synchronization mechanism, phase lock loop or similar. Grid forming inverter doesn't require phase lock loop for synchronization, but in some of the grid forming controls, you can find phase lock loop being used for synchronization of overall response of overall plan. Ability to provide black start, grid following inverters normally wouldn't be able to do that, and grid forming inverters, if designed with sufficient energy buffer and inverter overcurrent capability, can provide black start capability. Ability to operate in low grid strength conditions. For grid following inverter, you'll find the minimum grid strengths that grid following inverter is designed for. And as I mentioned, you can have weak grid package, so it's more enhanced controls to behave stably in weak grid conditions, but still there will be a limit, a minimum level of system strengths that's required. And grid forming inverter can provide, can operate stably in really weak grids and provide stabilizing effect for grid following inverters in that same area. Talking about maturity of this technology, grid following inverters are by now kind of well understood. There are commercially available products also for weak grid conditions, and standards exist for performance that's expected. And the latest standard, IEEE 2800, have been just approved with, with great percentage of acceptance. And then grid forming inverters, that's something just only starting. There is no agreement on performance that's grid forming inverter is expected to provide, and still being an active area of research. So we are finding ourselves in this chicken egg situation that I talked about in many previous presentations, but basically the question is what comes first, the requirement for capability or capability itself. And so how grid operators know what performance to require from new equipment, and if equipment will be capable of providing system needs. And in the absence of this knowledge, what happens, there is no incentive for this new technology. In the absence of this new technology, there are restrictions on the grid that system operator will enforce, and saying even so, what Christian was talking about, there is a minimum level of synchronous generation that will be kept online just to ensure stable operation in absence of any other technology. So then developers will find it difficult to integrate more and more inverter-based resources on the grid, because there'll be areas where no more can feed, basically. And then manufacturers will see shrinking markets, and all this time manufacturers don't really know what system needs are and what performance is expected from these new technologies, and so what to develop. Overall, controls can be designed in many ways and very flexible, but there is no common understanding of what actually is needed. Yeah, and then one point here kind of highlighted in red is just to say that inverter-based resources, they will only build to the requirement or market incentive. So one of the things I heard on very recent calls of NREL, Inverter-Based Resource Performance Subcommittee, is that even if a resource comes to us offering grid forming technology, we cannot actually accept it because we're using generic models and we don't have a model for grid forming inverter. So that kind of trivial thing, you would say, is a barrier for technology deployment. It's not very trivial. Deepak will talk more about that. But the failure to find an exit from the circular problem could hinder our ability to meet energy transition goals, and it can also increase costs of this transition. Around the world, there are thousands of solar, wind, and battery resources, and you have seen in previous presentations how big are the queues to connect to the grid. These resources, in absence of any clear incentives or requirements for grid forming capability, they all will be built as existing grid forming technology, and that will require additional supporting devices to be put on the grid to provide stabilizing effects. And so this is illustrated in detailed example in the appendix of the report, and I only have here kind of a schematic representation. So imagine you have a part of the grid where you only have inverter-based resources. So 3 resources, they are all grid following, solar storage, and then an external grid disconnects and you want to operate as an island. And so if all resources are grid following, this island becomes unstable and cannot sustain itself. So to provide this additional stabilization in island operation, you can add additional grid forming inverter-based resource, or it can be synchronous condenser or maybe synchronous generator to provide this additional stability to an island. And again, this is additional resource to provide stabilization to this existing 3. And then the island can operate stably after a external grid disconnects. But then on the other hand, if one of these resources from the beginning was installed as grid forming, same stability can be achieved in the island just by doing that. So you don't actually need this additional resource and investment into that. So that kind of to illustrate the cost of not acting now. So in the report, we kind of defined a way out from this chicken egg problem. And we think that one needs to think from, defining a target system, kind of where are we headed, what is the energy transition goal that we're trying to achieve in terms of, percentages of inverter-based resources or percentage of renewable technologies on the grid. Define resilience parameters that we can live with, and that kind of just parameters that system can operate stably and reliably with. Perform studies to determine system needs in this state, and then from that formulate technical requirements for system services. So kind of what services are needed for the system with this amount of inverter-based resources to achieve this amount of resiliency. And once these requirements are formulated, then equipment manufacturers will have clearer design parameters to design grid forming resources or any other technologies that can help provide these services. Then these services need to be quantified, and developer can evaluate and build projects that can provide the services. System operator needs to determine if it's more economic to require the services from everybody, or if services need to be implemented through market mechanisms. And again, it will provide incentive for developers as they design their projects. Technical benchmarking needs to be defined, so to be able to verify if inverter-based resource indeed can provide the services. Implementation process has to be developed, and then monitoring and performance as these resources are getting online and starting to operate, to understand if resources indeed are providing the services. So I just wanted to step through example of implementation in national grid. We actually developed this flow first, and then we realized that national grid and GB already following the steps kind of in the history of development and incentivizing grid forming inverters. So early on, they carried out a number of studies of system performance with large amounts of inverter-based resources, including up to 100% IBR. And this is consistent with the steps 1, 2, 3, so defining target systems, resilient parameters, perform studies. And then they developed performance requirements for grid forming capability. And so those were recently approved, and these are first in the world requirements for grid forming inverters. Again, these are non-mandatory and will be procured through market mechanisms. And this is consistent with steps 4 and 7, so formulate technical requirements and define benchmarking. At the same time, they launched a series of competitive tenders called Stability Pathfinder to procure new system services needed with changing generation mix, specifically system strengths and support for rock-off mitigation. And this is consistent with steps 5, 6, and 8, so quantifying system services, determining if it's economic to procure it or just require, and then defining technical, implementing services, sorry. And so along with evaluating the projects, offering into Stability Pathfinder, next steps will be to develop market mechanisms for procuring grid forming capability on ongoing basis beyond the Pathfinder projects. One thing I've just briefly to mention is that there is a trade-off between where system provides certain quality, so certain characteristics to accommodate inverters versus inverter provides certain characteristics to fit the grid. And there is a balance somewhere there where the system needs to guarantee certain characteristics, and so that inverter can be designed for this. Because if the system will keep being always changing target, then you always kind of chase it with inverter design. So as system operators are evaluating system needs, that's something to think about. So kind of like, where are we going to stop and design the system for inverters, and where inverters need to be designed for the grid. Just briefly to mention, there is a chapter about the tools in the report, and basically in the center here, there are stability tools that are used today. And in the center of this are positive sequence, phasor domain tools. These are still very important, and they will continue to be used because they allow you to do thousands of simulations for different system conditions and contingencies. Increasingly, EMT type of tools are gaining interest, and then also phasor frequency domain tools are also being used for control tuning and understanding of stability range of inverter-based resources. All of that being said, the quality of models doesn't define quality of tools. So you can use very good, accurate tool that allows very detailed representation, but if model is not accurate or detailed enough, then the tool is no good. So sometimes the model can be really good, and even in the phasor domain tool could be sufficient to represent certain behavior. So always you need to think about accuracy of models, and then what tool to use for for what type of study. EMT and frequency domain studies, they are limited to smaller portions of the grid, whereas phasor domain positive sequence tools have been used for a long time and allow bigger grid representation, allow a lot of scanning studies to be done. Analytical tools that are being used to process the results from this stability tools, these are also developing further to represent some of the phenomena with high shares of inverter-based resources, but also increasingly what you see on the left-hand side, economics tools are becoming important, kind of tie into the stability tools. Before you would kind of think about these tools separately, and you would do economic analysis, resource adequacy analysis, everything separately, but also increasingly now stability constraints are putting additional constraints that affect resource adequacy and production cost simulations. But on the other hand, production cost simulations, resource adequacy assessment provides initial conditions that need to be assessed in stability studies. So there is tighter bind between different tools that needs to be done. And we are starting a task force. You can hear more about it on Thursday, joint task force to work on what are the needs of this more integrated planning process and how different tools can be tied together. So just some two conclusions. Grid forming technology is one of the necessary enablers for high inverter-based resource penetration. It's certainly not the only one. Not all inverter-based resources need to have all possible characteristics. That's the point I was trying to get out of Christian to confirm. We propose step-by-step approach of defining and implementing new system services. Early adopters such as GB are already breaking the circular problem through defining services based on system needs, and this provides clearer indication to inverter manufacturers what needs to be designed for grid forming inverters. It is recommended that future still early adopters think about defining requirements at higher level, and then all the details about how performance is validated go into some kind of technical guides, and that's again what's been being done at GB. Grid forming capabilities in batteries is a low-hanging fruit. It's basically a control function. There is no need to add additional storage. The storage is already there, so there is a buffer that can be used for grid forming functionality, and controls can be designed to be grid forming. So not incentivizing it today may result in additional costs in the future because synchronous condensers or other devices would need to be installed to provide synchronizations. Further reinforcements of transmission system will still be necessary to enable long distance high power transmission from remote areas reached with renewable resources. So grid forming will not solve your long distance transmission issue. And with higher shares of inverter-based resources and new technology, there is a need for further development of tools and tighter integration of tools and improvement of modeling. So thank you very much for your attention. You again see the link to the report here. One thing I wanted to mention on Thursday, we are also kicking off a continuation of this work where we're going to look at system needs, system services, and how the services need to be defined, preferably in technology neutral manner, so that any capable technology can come and provide. So we are going to work on this year. Thank you.
Thank you, Julia. Excellent. And thank you for walking us through that. Again, please feel free to go to the ESIG website and download the report. We have the full report and some shorter versions that are available as well that will be there shortly and available.
I just forgot to thank everybody who contributed to the report. There were about 30 people, and thanks so much for your participation.
Yeah, I echo that. Thank you. A lot of hard work went into this. And next, I'd like to introduce Dr. Deepak Ramasubramanian. Deepak is a technical director at the Electric Power Research Institute in the Grid Operations and Planning Group. Deepak joined EPRI in 2017, where his work was in the area of modeling, control, and stability analysis of the bulk power system, with focus associated with the impacts of large-scale integration, converter interface generation with grid-forming inverters and DER. He received his PhD degree in electrical engineering from Arizona State University, not too far away from here, in Tempe in 2017. I also have to say, Deepak's outstanding contributions, not only to ESIG and the reliability working group and everything that we have here, but across NERC, across IEEE, CGRAE on this subject are just phenomenal and groundbreaking. So thank you, Deepak, for your leadership.
My pleasure. Am I audible at the back? And yeah, so as Jason mentioned, I'm a localite to Arizona. No offense to Tom here for Northern Arizona University, but ASU Sun Devil. So what I'm going to be talking about today is kind of continues what Julia was also mentioning regarding the modeling and regarding the type of models that we can have for grid forming devices, and talk about some of the work that we've been doing on developing positive sequence models to represent these kind of resources. And I like to start usually any presentation on modeling with this kind of a table, because as Julia mentioned, it completely depends upon the tool that one is using, the model that one is using. And an EMT model is not necessarily a good model. An RMS model is not necessarily a bad model. It completely depends upon how the model is constructed, how the model is parameterized, for what kind of study is the model being used, how has the model been validated, and how has the model been do you have the correct components implemented, do you have the correct control loops implemented, and so on. And when you have all of these components implemented in an appropriate manner, in a sufficient manner, then you can utilize the capability of a simulation environment to the greatest extent possible, and you're not limited by the model limitation that may exist. And where this helps us, or where this kind of an ideology or notion helps, is in the development of generic models. We've heard about synchronous machines. We've heard about how Christian mentioned that one of the aspects that they want is a grid forming inverter to be like a synchronous generator, but be much faster, or be much more than a synchronous generator. But what we have to identify there is it's not just the synchronous machine by itself. It depends upon the associated controls that are related to the synchronous machine. And here's a very simple example that helps denote that. If you have a synchronous source or an inverter-based resource connected to a network, and you have a variation in short circuit strength, if you take that synchronous machine, and we all take it for granted that a synchronous machine has an excitation system control that controls voltage and provides field excitation. But if we remove that excitation system control from a machine and keep the same machine, so it has a voltage behind impedance, it has a rotating component, it has the electromagnetic force, it has the inertia, but we replace that excitation system control with a control that tries to control the Q output of the machine. So it will not allow the machine to increase its Q output greater than a reference level. That same synchronous machine is unstable like an inverter-based resource at the same short circuit strength. So what it comes down to is, and in the machine and in the inverter now, if you replace that with V control, as shown by the red and the orange curves on this graph, then you get the same profile of stability, even though the inverter-based resource has a PLL, has current control loops here. So what we realize from this is that the way the machine or the resource is trying to synchronize to the network, the kind of behavior that it exhibits, that synchronization component is not necessarily the cause of instability, but what the cause of instability is the fact that that resource, a grid following inverter, is actually trying to control its Q output and not change the Q output when the grid conditions change, which happens in a synchronous machine also. And that kind of a notion helps us to develop control agnostic performance requirements for grid forming inverters, and it helps us develop control agnostic models and generic models for grid forming inverters. We take that to the small signal domain, we take that to the frequency domain, and we see the same kind of results coming up. When you have an inverter-based resource with a PLL, with an inner current control loop and with a Q control associated with it, we see instability starting to come up from a small signal sense and a time domain sense when we start reducing the short circuit strength. But that same control, the same structure, if all that we do is replace it with a voltage control, keeping everything else the same, even from a small signal sense, we can start seeing the eigenvalues move to the left half plane. We can start seeing an improvement in stability come up. We can start seeing an improvement in the way that resource is able to remain synchronized to the network as the system strength reduces. This brings about this fundamental property that what we are trying to establish is that grid forming control, yes, we want a voltage source behavior, but more importantly than that, we want it to be able to robustly control voltage and robustly control frequency. Once we have that kind of a requirement or a concept in place, it then becomes easy from a system planner perspective to be able to define how we want to test that, how we want to verify that, and how we can develop control agnostic specifications for that kind of behavior. And we use this to develop this generic model in positive sequence. It's a collaborative effort across EPRI, University of Washington, University of Illinois, Urbana-Champaign, and University of Minnesota. And what we did from this perspective is that from the context of our model, grid forming is defined as this resource that can transiently change its current injection to help control voltage and frequency. As a result, yes, the voltage phasor remains constant in the transient time frame, but what it is doing is it's allowing the current injection to vary when the system condition changes so that it's giving the system what it needs. And as a result of that, we get about an improved stability. And then in the same model, we can now represent 4 different types of grid forming control, all within the same model, which a system planner can choose to enable by changing a flag setting. And you change this one flag setting, you get a different control type. And we have 2 types of droop control, one based on a PLL with synchronization, as shown on the two slides before, one as a dispatchable virtual oscillator and one as a virtual synchronous machine. All 4 types of grid forming control, as we'll see later on, can exhibit similar performance characteristics, and they behave in a very simple manner. And this model can be interfaced with the existing plant controller models that we have today in our software like PSSE or PSLF, so that if one is trying to change the way a solar plant or a wind plant is going to be represented, we can just pull out one of the existing modules and put this new model in place, and planners can run large system studies with these type of models. This is the model. The block diagram looks scary, but the reason the block diagram looks scary is when one writes a mathematical equation. You can write a mathematical equation with various terms, but if you want to translate it to a block diagram and ensure there is no overlap in lines, ensure there's no lines going across the figure and things like that, the block diagram becomes challenging to develop. But the underlying property of the model is actually governed by 3 equations. And I'm happy to talk offline about those 3 equations if we have, and there are references put at the bottom of the slide. So just by changing one flag, we can change the type of grid forming synchronization element that we are using. We can limit the amount of fault current that is being injected by this grid forming device. We can control power limits. We can interface it with a plant controller. And we can get all the properties that we want from this grid forming resource from this model. So this is a generic model that we have developed. We are, of course, not the only ones. There are other research organizations that are also doing a great job in developing these models. And our goal is to try to harmonize them together so that we can make it easy for planners and operators of not having too many models in the software for use. But that's an ongoing process. I don't want to spend too much here. What we saw was that this model that we have, the number of parameters that we have, this is a question that we get a lot from planners and operators, that, oh, the model has a lot of parameters, or oh, there's too many parameters. How do we know what value to give to these parameters? And how do we understand what functionality each parameter is doing? So the way we have structured this model is that it has only 5 additional parameters in comparison to the models that are available today. And these 5 additional parameters, of them, 2 parameters are related to droop coefficients, which can be taken from standards, or they're also available in other models that are used for existing plants today. 1 additional parameter is a flag setting, which depends upon choosing which control type to use. And the final 2 parameters are to, if you are using a virtual synchronous machine mode, you define the inertia and the damping constant with it. So overall, the additional complexity or burden in terms of number of parameters that are there in this model is not too great compared to the existing models that are already there in software. We have a document there which is linked, which provides the entire list of all parameters and what values and so on. But this is how the model behaves. And as you can see, because we are exploiting the fundamental behavior of the voltage control at that fast voltage control at the inverter level, all four types of group across, all four types of grid forming across EMT domain and positive sequence domain are showcasing similar behavior. And it's very difficult to even identify the different curves from each other. And that's the kind of control agnostic property that we want in a generic model. And that's the kind of control agnostic property we want in performance requirements, so that once a performance requirement is specified, the equipment manufacturer has the flexibility to use whatever kind of method they want, as long as they can meet the performance requirement. And then the performance will be similar to any other grid forming device, which also tries to meet the same performance requirement. And the representation of the model is consistent across both positive sequence and EMT domain. Now, a caution here is that we're not trying to say that positive sequence domain can show every detail or every kind of behavior. We definitely recognize that EMT models are important, but it's about exploiting the capability which we can get from positive sequence domain and exploiting it to the greatest extent possible in order to do studies at a system-wide level with these different resources. And that's where these new models that we're developing come into great use. The same kind of consistency is represented as we go across larger systems also. So this is a standard IEEE 14 bus network where, again, we have 5 different grid forming resources, different types of control, comparing against both positive sequence domain and EMT domain. And again, you can see that the results are matching very well, both for load increase and decrease, for fault events in the system. And what's more important is there's no synchronous machine at all in the system. So it's completely started up from no equivalent voltage source, no synchronous machine. Start it up in a black start mode, run the event, let the system come to a stable, steady state, and then run the events following that. We compared it against an OEM. We can't name the OEM, but we have compared the model against an OEM's black box model. So OEM, for those who may not know, is original equipment manufacturer. So they are the ones who develop or create these inverters and so on. And we tested it against a black box model from this OEM. And first thing that we see is we don't expect an exact match in the response, because we don't know what's inside the OEM's architecture, and we don't want to know, because the main thing here is an OEM is allowed to keep their IP, is allowed to formulate their grid forming in the way they want it, as long as they can meet the performance requirements. The goal here is, can the generic model represent the trend of response that we see, so that if a system planner is using this generic model and sees the trend of simulation results that they observe, they're able to make conclusions regarding or inferences regarding the study that they are doing. And as we can see, across load increase events, across fault events, the generic positive sequence model is tracking well the trend of response that we see from the OEM black box model. So it's encouraging from the perspective of the type of model that we have. Of course, there's more work to be done, but definitely we know that this is the first step in a long road forward, and planners can now start using this model to understand what can happen in a system with more inverter-based resources. This has also been translated to the WEC system, so the entire Western Interconnect. We replaced an entire area of the Western Interconnect with inverter-based resources. And then the blue curve is if it was with synchronous machines, the red curve is with grid forming inverters. And the event that we applied was made that area very weakly interconnected, so that there is these oscillations come up, but grid forming inverter can help stabilize the network in that kind of a condition. Presently, we have these models available across different type of software. So the type of software that you might be using for your studies across positive sequence domain, EMT domain, a little bit for distribution network simulation studies also. We have this model structured across different kind of simulation domains. Some of them are even from the perspective of having the switching level model implemented or code-based model implemented, where you can directly translate code from the inverter to the software and see the representation that we will have. Where these kind of models, where these kind of models can be used is to evaluate size of grid forming device, percentage of grid forming resources, and location on the system. And this is one example where we have used it where we have a positive sequence simulation compared with an EMT simulation for a small system. The top half shows without grid-forming inverters, the kind of oscillations that we see between synchronous resources that are coming up. They are lightly damped. We add the grid-forming inverter for the same fault. The oscillations are well damped, and the positive sequence response tracks the EMT domain response. This is the same system that Julia showed in her presentation, only taking it to the level of now actually looking at instability come up in this kind of a network, where you have 3 grid-following inverters labeled as IBR, and you have the system equivalent. And if you actually disconnect that system equivalent, as Julia was mentioning, you can get an instability in this network because of the fact that all of these grid-following devices are trying to control P and Q rather than trying to control any kind of voltage. But if we now have to add an additional device, or if we have to add a grid-forming property, we can now utilize small signal domain tools, and Vahan's also going to talk a little bit about it. We can utilize these kind of frequency domain characteristics and properties in order to understand how to size the grid-forming device, how to derive the control components for it, how to understand stability for the network, and how to understand as you go from slow voltage control, which is the blue dots on the left half plane of the S-plane, to fast voltage control, which is the yellow dots, how the stability characteristic improves in the system, which is also reflected in the time domain characteristics that we have. Just a brief note, when we are looking at black box models and we are looking at evaluating frequency domain properties and we're looking at stability, there are nuances to be kept in mind there regarding power flow operating point that it's going to be evaluated at, regarding the type of system in which you are evaluating it, regarding the type of state space representation that you create for that kind of a model. And especially when we go to frequency domain and state space domain, we have to be very careful about overfitting a model in terms of how we would characterize the number of states and the number of eigenvalues that we would see. And transitioning this to an island power network where we have tested the operation of this model is in PSSE, look at the performance of how an island power system runs purely on inverter-based resources. So this is an extension of the small systems that we're seeing. This is a real island power network of one of our utility members. And looking at their network, we can then see that comparing the performance between having a synchronous condenser versus having an grid-forming inverter. And these are the kind of studies that a utility might want to conduct numerous studies to understand whether they need to apply a synchronous condenser, whether they can replace it with a grid-forming inverter, what kind of size of the grid-forming inverter do they need, where do they need to apply the grid-forming inverter, how to parameterize it. They can get all of these understandings with these kind of positive sequence models. The example here shows, of course, that when you have a grid-forming inverter as opposed to a synchronous condenser, you have a much better performance. So just to close out, what I wanted to talk about today is the development of these generic models. They go from, because we're developing control agnostic generic models, we go from the very fundamental level of understanding what exactly is happening, what is the property that we need, what is the kind of performance that we need. We identified here that Q control at inverter level is what is the root cause of instability. Moving to V control is what helps improve stability. We have this preliminary version of the positive sequence model. Happy to chat offline if anybody is interested in using these preliminary versions of these positive sequence models for system studies. Tested it against black box models. And these models can now start being used by planners and operators to understand how grid-forming inverter deployment is possible on the system, and use that to translate requirements back to the OEM. So kind of it breaks again the chicken and egg problem, because now you have a model available to start doing studies. One last thing is this is a work that we're continuing to do. We have this grid-forming consortium, which is set up now. It's a Department of Energy funded consortium co-led by EPRI, NREL, and University of Washington. What this consortium is going to do is it's going to bring together a diverse set of stakeholders. We have an entire team which is assembled across national labs, universities, manufacturers, utility system operators. And this is going to be an initial 5-year effort where we're going to collaboratively work towards expanding the notion of grid forming, expanding the understanding of grid forming, the modeling, the control, stability analysis, hardware and validation, demonstration. All of those we're going to roll into this one project and bring together these different stakeholders so that we can develop this grid forming technology further on. If you're interested in knowing more about the consortium, please do let me know, and I'll be happy to provide information. With that, Jason.
Thank you so much, Deepak. Yet another demonstration of how we're moving the needle forward to evaluating what the capabilities are and how they can be studied, how they can be looked at in terms of meeting some of the grid needs. So modeling, obviously super important. It's something that we're also digging deeply into with the reliability working group. And as Julia said, really also looking at how this fits into an integrated planning process to identify when you need it, how much you need, and what the performance characteristics are. So with that, I'd like to also invite our third speaker, certainly it's last, but certainly not least, Vahan Gevorgian. Vahan is a chief engineer for NREL's Grid Integration Lab at the Power Systems Engineering Center. He joined NREL in 1994. And Vahan leads many research projects funded by various DOE programs and collaborative projects within the industry. And Vahan, we've done this many times before, right? We're here to talk about the things that we do, not only to look at capabilities of technology, but how we test them. And Vahan has really been an industry leader in developing a controllable grid interface at NREL to understand how these capabilities can actually be realized, and what is their performance on the grid, and how does that also go into developing some of the models. So we're full circle about capabilities to actually demonstration, and would like to hand it over to Vahan.
Thank you, Jason, for introduction. And good afternoon, everyone. Higher. Is this better now? Okay. I'll try to keep my mouth close to my collar, basically. Yeah, so just echoing the previous speakers on the issue of grid forming, as in a power system, the levels of penetration of the wind and solar are going higher and higher, and they are becoming essentially the mainstream generation sources. And in fact, they are also are capable to provide all type of grid supporting services. And in many places, that instantaneous penetration level is pushing very high, 60, 70% or even higher. The question is, what type of fundamental shift we need in a way we operate power system to push even beyond that and be able to operate large bulk power system with only few remaining generators or even without generators. So whether is it a big system or a portion of a system. And then the main question there from reliability standpoint becomes how to operate the inverter-based resources to maintain the minimum acceptable reliability levels. And then another question there, how the grid forming resources, what role they can play in it. So in a system with high levels of penetration is named by many studies, the issue of a grid strength is expected to become the main stability deteriorator. And the grid forming resources as being a resource that can, with their fast response and ability to track the load, and also the fact that, for example, the simple Drupe-based grid forming inverter is a first order system compared to the grid following inverter with a PLL, which is a second order system. So grid forming resources are expected to have better stabilizing impact on the grid. So here is a list of the issues that we expect to see in a weaker grids. And all of them are essentially in one way or another are caused by the grid strength. So how inverters can help to address these issues? Perhaps they can help addressing or mitigating some of them. But the main issue of a grid strength, where you have number of resources with a current limit, the issue of grid strength probably cannot be resolved with inverter resources only, but stability can be improved by use, for example, of grid-forming inverters. So in order to increase the grid strength, there are other solutions. For example, the over-80 inverters, which is costly, or as it was mentioned before, deploy the synchronous inverters in a large scale. So the question, the other question is also how we maintain the resiliency of a system or enhance it, how we do a black start of a system, how we operate in islanded conditions. And these issues also are related to the grid strength, along with the things like protection adequacy. So how grid forming inverters are going to help, how many of them we need and where in the grid we need, how we control them. Do we need large capacity of those inverter, or we need a smaller capacity but control them in a different way? So those are the high level questions that we're trying to address by a number of studies at NREL in collaboration with other national labs and industry, and is basically one of the large or the major research efforts going on in the industry. So we've been doing a lot of work in this area. One particular project, which is the ongoing work between NREL and GE, project funded by the OE WITO program, is the demonstration and testing of the grid forming inverter based on a type 3 wind turbine drivetrain, doubly fed induction generator. To the best of our knowledge, this is a first project of its kind. The grid forming in a wind has been demonstrated in the past by Siemens and Gamesa on the type 4 machines, but this is basically the first type 3 demonstration at the utility scale. So at this stage of a project, we deployed that drivetrain on NREL dynamometer and perform a number of tests to characterize the controls developed by the GE. This is the electrical diagram that explains more in details what the setup looks like. On the left, it's NREL 7 megawatt grid simulator or controllable grid interface, which itself is perhaps the most sophisticated grid forming inverter in the world, and it is attached to GE 2.5 megawatt electrical components of GE 2.5 megawatt turbine drivetrain that operate with a grid forming control. In this setup, we are able to emulate different test conditions under totally controlled grid environment, such as varying grid strength condition, balanced and unbalanced voltage fault conditions, frequency variations, phase jumps, and also demonstrate the islanded operation. And this particular setup is fully power hardware in a loop enabled using our RTDS system coupled with the grid simulator. So the project has already been passed through its first stage. So the grid forming machine was fully characterized and demonstrated exceptionally stable performance. Here are some examples of a test. For example, the zero voltage ride through event emulated by the grid simulator, and you can see how the type 3 machine goes through it. The one on the right is the 30 degrees up and down phase jump. So this, the transient performance of his machine basically demonstrates how the grid forming resources work. Almost instantaneous response to the faults and phase jumps in the form of both active and reactive power, whereas in a grid following mode, this response would be much slower. We also validate the models, by this effort, validate the models, transient models of this system, both in a time domain and also in a frequency domain. This is the example of a measured and simulated impedance characteristic of a generator, and you can see that they show pretty good match. Why the frequency domain simulation is important? Because we are using this type of data to actually understand what are the stability impacts of this type of technology or any type of inverter on a grid using the Nyquist stability criteria. And then we have a methods that allows us to go from impedance stability analysis down to a small signal stability analysis. On top of the characterization of the controls, we also have a large research agenda with that, where we're going to test the type 3 machine in parallel with other technologies to understand interactions between grid forming wind with other grid forming resources, such as the grid forming battery, other grid forming wind turbines on a system, and also operate it as a multi-technology island or microgrid. Here is one example of the black start of a grid forming turbine using the actually grid-forming battery energy storage. So black start and grid forming is two things that I think needs to be distinguished. The resource can be a grid forming, but not be a black start capable. Same way like many synchronous machines are grid forming, but the certain type of power plants are not black start capable. So in this case, you need the energy storage to black start the turbine to be able to maintain a load in an islanded operation. So this is an example of the you see on a second graph from a bottom. First, we started the battery that is feeding the load. At the timestamp 2, the turbine synchronizes with the grid. At timestamp 3, it starts generating. And then at timestamp 4, the battery, so basically the system is operated at a variable load, and wind is balancing the load. And when the wind power is not enough, the grid forming battery comes into play. And we have been operating this in islanded standalone mode with a almost 3 megawatt load for extended periods of time. How the grid forming resources can interact with each other. This is one example of parallel operation of a grid forming turbine. And so it's a measured data and a grid forming battery. So you can see at certain combination of droops and control parameters, when a system is disturbed, it goes into some sort of a on-damped oscillation mode. This particular one is about 11 hertz. And so how to predict this type of behavior? Grid forming resources or grid forming resources with grid following one can interact with each other. So again, I mentioned the impedance characterization testing of a machine to get the characteristics in a frequency domain. We have been fully able to predict this type of behavior by conducting the impedance scans of both resources, and basically for this set of control parameters, identify this 11 hertz oscillation. You can see the plus minus 11 hertz resonances below and above 60 hertz. So this is totally predictable behavior, assuming you have validated model of these resources. We also perform a lot of simulation studies for a grid forming wind and other resources as well. This is one of the test cases we use to understand how the grid forming wind can help to improve the stability of onshore networks if we are talking about a large offshore wind power plants. There is a model of the large offshore wind power plants connected with the grid via submarine cable and with a shunt compensation, with a grid forming battery and synchronous condensers. There is a number of resources that you can activate if needed, depending on which scenario you are simulating. There is an example of when the grid connection is broken, and it trips, and the whole offshore wind power plants is operating in an islanded mode, feeding the loads in a coastal grid. And the transition happens, in this case, at time equals 1 second. You can see that the grid drops, and the grid forming plant picks up a load immediately. We're also using the synchronous condenser to increase the grid strength, because this was we simulated really weak grid interconnection. But the transition is very stable, and then as load is varying, the offshore wind is able to follow the load, and then if necessary, the point of interconnection battery can kick in as well. We've done a number of simulation understanding how this type of a grid forming wind plants can provide a ride-through. This is a case of the non-symmetric ride-through, and you can see on the bottom plot, the wind turbine goes into the current limiting mode when the fault happens. So the current limiting is another important aspect of a grid forming operation, because you have to limit the current, otherwise you're going to damage your semiconductor switches. We're looking at a number of different ways to control methods to limit the current. Two main ones shown here: direct current control, which is faster, but is prone to saturation, or the virtual impedance-based control. And we are currently testing both these methods in a model, and eventually we'll be testing it in a real hardware as well. In order to understand what is the impact of this type of controls on a stable operation of a grid with the number of inverter-based resources, inverter grid, including the grid forming ones, we developed the impedance scan tool in the PSCAT, which is basically a software model that you can plug in anywhere into a model of your power system and scan your generator and scan the impedance of the rest of a grid. and then basically understand at which particular frequencies the interactions can happen, so you can mitigate those and introduce damping in early as possible stages, preferably during the planning stage. Here is one example of how we identify that. This is a multi-bus system which goes into the oscillatory undamped mode after the voltage event. And then we use the impedance tool basically to understand, who is causing this type of instability and how much grid forming you need to damp it. So that's the main characteristic of that impedance scan tool, that it allows to understand who is causing the instability and what you need to do to damp it. So this is an example of how the tool is used. In the first graph basically shows the base case, where you have the grid forming resource and you see the long the process to damp the oscillations. But then after analysis, where we have been able to increase the bandwidth of grid forming controls, and in the middle one, you see that oscillations are damped pretty fast. But if you don't do it right, or you put a grid following resource, the system goes totally into unstable mode. And this is another example of how we measure the impedance characteristics of the inverter-based resources. This one basically compares the impedance characteristics of a same inverter in grid forming and grid following mode. So we're using this type of information basically to, along with the impedance scan model, to understand how we can improve the stability of a system using a different type of control modes. And the last but not least, in terms of wind, we have also been looking at so-called Type 5 wind turbine generators. This technology has been around for the last 30 years, but it didn't gain popularity because of a couple of the mishaps they had in the field in early 2000, and simply because the vendor who was doing it, they adopted completely wrong system and wrong control. But this is getting more traction in some places in the world. And Type 5 machine is basically a variable speed wind turbine, but uses just a synchronous machine directly coupled to a grid. So power conversion is happening on a mechanical side. There are a number of these machines operating in the US still, and actually 10% of New Zealand's wind generation is Type 5 machine, have been operating for the last 5 years in a very reliable way. So this is basically another way to, for a variable generation to contribute into improvement of a grid strength and bring all the benefits that are related to a conventional synchronous generation. Like a table on the right compares all the grid integration challenges, and almost in every aspect of it, the Type 5 machine has an answer, yes, yes, yes. Means it has a superior performance, including the ability to operate as a synchronous condenser by the time of no wind. So we have a funded project from DOE, WITO, to look at the system level benefits of Type 5 machine. And in fact, we'll be also doing some demonstration testing at our facility, because we also purchased a real synchronous machine to do so. If people who are interested more in this, we just published a paper in Electrification magazine. The link is shown below. I can share it later, whoever is interested. So at the end, as a summary and conclusions and future plans, so grid forming technology by inverter-based resources is gaining more and more interest in the energy industry. For some technologies, like for battery energy storage systems, essentially it is ready for prime time. It's already in a prime time. There are a number of battery inverter vendors provide the grid forming as a standard control option for the grid forming inverters. So we do a lot of work, is still in a research area to understand how the grid forming from wind and solar inverters can also help a system in this transition. The mainstream wind power based on Type 3 and Type 4 turbines are fully capable of providing the grid forming services. We demonstrated one with the Type 3, and as I said, Type 4 was demonstrated earlier with the Siemens Gamesa. Grid forming resources are fast acting. They are providing stabilizing services, and their value is going higher as the level of penetration increases in a power system. So as a major future step, we are envisioning the large-scale field demonstration of the grid forming operation for both wind and solar and storage for that matter. And we are working with a number of industry partners in that area. And of course, the standardization of these controls would be also the major requirements in the future. This is it. This is all I wanted to share.
Excellent. Thank you very much, Vahan.